Good evening, everyone. Am I audible? Good evening. Hello. Okay. Thank you. Okay, so I hope let's start today's session. It's already the time. So today we will cover the week 3 mostly. It includes group and some related things like cyclic group, subgroups and all. So we will start with one problem. So in between, if you have doubts in concept, so we will explain the concept also in between related to the particular question. So the first question is the number of singleton generators of the cyclic group Z plus is infinite 1, 2, 3. So first of all, we should know what is the generator. I hope you might have seen already the videos and so you know the definition. Anyhow, let me just explain once what does a generator means. Okay. So if G is a group, if G star is a group, then A is an element in G. It is called a generator if A generate whole G, that is set of all A power n such that n in Z. We are taking all the powers of A square, A cube, etc. and A power 0, which is the identity, and the A power minus 1, A power minus 2 and so on. So if we are taking all these elements, obviously it will be a subset of G for any A. So if there exists a such that if all these elements like A power n, all these elements is same as the group G, that means A generates all the elements of G. In that case, we will say A is a generator. So the singleton generator means like it is same as the generator, that is just one element which generates whole G. So the question is how many such generators are there in the cyclic group Z plus. Okay, so if there is at least one generator, then that group is called cyclic group. So obviously cyclic group they are saying. So we know one generator of Z plus, obviously everyone knows. Okay, so how many generators are there? Can anyone tell? How many elements generate whole Z, whole integers under addition? Any idea? So you can start with some particular element. Okay, for example, I am considering 0. So what are all the elements generated by 0? Okay, here the operation is addition. Okay, what I have written it is A power n. A power n means what it says? N times A star etc. A. Okay, the star is the underlying operation. Okay, it is not the product A square like that. Okay, it is the star operation. So here in this case we have addition. So what does the A power n means? N times adding A, or we will notate it as Na also. But the standard notation is A power n. A power n simply means A star, that's all, not the usual dot product. Okay, so here the generator of 0 means first we will take 0, then 0 plus 0, 0 plus 0 plus 0, etc. Okay, in the opposite way means 0 minus 0, that means a power minus n terms. It should also come, right? 0 minus n 0, 0 minus 0 minus 0, all things like this it will come. Okay. So this just gives the 0 element only. So it is not a generator. If 0 gives all the elements of G under this operation 0 power n, then it is a generator. Okay. Now can anyone tell one generator of Z plus? At least one element which generate whole Z. Any idea? One. Good. So the simplest element, the standard generator of Z is 1. Okay. So generator of 1 means what we will get? 1 adding 1, 1, 1. Okay. First 1 we have 1 plus 1 is there. That means 2 times 1. 3 times 1. 4 times 1 and so on. So. Okay. So what is 1 power 0? 1 power 0 means identity. Okay. 1 power 0 means identity 0. And in the negative sense, what we will get? Minus 1, minus 2 and so on. So. Okay. So 1 is a generator. Okay. Now, can anyone think about any other generator for this one? Okay. What about 2? Does 2 generate whole Z? Yes or no? Yeah, minus 1 is a generator. Okay, minus 1 is a generator. Very good. Before that, let's go to minus 1 before. Okay, alright. Minus 1. Minus 1 is also a generator. One thing we can say is, if A is a generator, the inverse of that is also a generator. A inverse. That's already we have seen as a theorem. Okay. Here 1 is a generator and its inverse is minus 1. So minus 1 is also a generator. Okay. That is one way to tell minus 1 is a generator. Otherwise, in the same way, we can consider minus 1 and minus 1 plus minus 1 is minus 2. Minus 1 plus minus 1 plus minus 1 is minus 3. In one side it will go like that, and in the other side minus 1 minus minus 1 it will come 0. Minus 1 minus 1 2 times. Okay, it's subtracting. In that case we will get all the positive element 1, 2, 3 etc. So minus 1 is also a generator. So minus 1 is also, we can write it as Z. Now, so we got 2 generator, 1 and minus 1. Now the question is, does there exist any other generator? For example, I am considering any integer, say 2. Does this, yeah, 2 will not generate. The reason is, it is like from here, by intuitively it is clear, right? First we will get 2. What are the generator? 2 we will get 4, 6. We are adding 2, 2, 2. So all the odd numbers will not be in this set. Okay, will not be there. So it will not cover whole G. Here also in the opposite way, we are getting all the even numbers only. So if we are taking any other element other than 1 and minus 1, we will get the multiple of that particular element only. Okay. So all other elements which are not the multiple of that element will not come in the generator set. So only 1 and minus 1 are generators. So this set has 2 generators. So the answer is 2. Okay. I hope it's clear for everyone. It has 2 generators and we have found that what are all the 2 generators. Now the question is number of all distinct subgroup of the cyclic group set 2027 plus. Here plus means addition modulo 2027 as I told in the last week. Okay. So number of distinct subgroups of the group set 2027. How many subgroups are there? So at this moment I may give you one hint I will give you. Actually that particular theorem will be covered in the next week. If you have seen the week 4 already, you might have that is Lagrange's theorem. You will go to the theorem and the proof in the next week. I will just state that. So using that theorem, you can easily tell the answer of this question. If H is a subgroup of G, then order of H, that is cardinality of H, divides cardinality of G. Okay. So now I think this question you can say easily using this theorem. Question is the number of such H, number of subgroups H of the group G, which is set 2027. Okay. The number of such groups, subgroups. Any idea? Okay, if H is a subgroup of set 2027, okay, then by this theorem, what does it means? Cardinality of H should divide cardinality of G, right? What is the cardinality of G here? 2027, correct. Because set 2027 means it starts from 0 up to 2026. So total 2027 elements are there. So we need to find the number of divisors of this one. Okay, if H is a subgroup, then it divides the cardinality of G. Okay, but 2027 is a prime number. It is a prime number. So how many possible divisors are there? That are the possible subgroups, right? How many possible divisors are there? 2. Because 1 is the divisor and the 2027. 1, 2027. Okay. These are the possible cardinality for the subgroup H. Okay. If I am taking 1, can you say any subset of the given set 2027 with the cardinality 1? What is that subgroup? The possible cardinalities for a subgroup. Okay. Now we should ensure that with all these 2, 1 and 2027, there should exist. We should convince ourselves that there should exist a subgroup with the cardinality 1 and with the cardinality 2027. So cardinality 1, the subgroup with the cardinality 1 is the identity subgroup, right? I am taking just the identity. It is a subgroup of set 2027. That is, what is the identity here? The 0. Correct? Just the identity element. It is a subgroup, right? And now can you say what is the subgroup of the set, the group set 2027 with the cardinality 2027? That's easy, right? Yeah, the G itself, the whole group itself. Set 2027. So only we have 2 possible distinct subgroups, and out of that we got with both this cardinality, we got what is that subgroup. Okay, so we specifically found the subgroup. So we got 0 and set 2027 are the possible subgroup. So the distinct subgroups are, number of distinct subgroups are 2. Okay, any doubt? Yeah, option C. Okay, now we will go to the third question. It's like very easy question. It's just a definition. You can answer it very quickly. A group is said to be an abelian group if which condition is satisfied? Yeah, of course. A. Abelian means the commutativity is satisfied. Commutativity means A star B equal to B star A. Like the order we are doing the operation does not matter. Not the order like A star B and B star A. It should be same. So answer is A. So I don't think there is an explanation is needed. It is just the definition. Okay. Now the next question is, a binary operation is given. So binary operation we have already seen. It is just a function which maps some g cross g to g, correct? So if we have two elements, then star maps a b to some other element in the same group or same set. Okay. Now here the given binary operation is a star b as 6a power 4 minus 9b power 4. If a and b are given, this is the binary operation. It is defined on R. Okay. Now the question is, star is commutative or not? The question is whether this is true or false. That is whether it is commutative or not. That means question is a star b equal to b star a. False. Okay. So again it is like if something is false, we just need to give one counter example only. Okay, if it is true, we need to prove it in general. If it is false, we can have two elements such that a star b and b star a are not equal. So simply we can take some two simple elements. For example, I am taking 1 star 0. So 1 star 0 means a is 1 and b is 0. So the thing is, instead of a I will give 1, instead of b I will give 0. So it is simple, it is 6. Okay. Now b star a, that is 0 star 1. The other way. The other way it is a is 0 and b is 1. It is equal to minus 9. So these two are distinct. A star b and b star a are a star b, b star a are different. So not commutative. Okay. So the question was whether it is commutative. So the answer is false, right? Okay. Now the next question is, again star is a binary operation and defined like this. The question is a star b star a. What is this? Here it is given as, first we have to do a star b, then star a. So what will be the answer? It's also a very simple question. A, B. Okay. Okay, while doing the calculation, be careful. Let's see what is A star B star A. Yeah, sorry, it's B. Okay, it's fine. So, first we need to check what is A star B. A star B, by definition, it is 4AB. 4AB star A. Okay. Now, instead of A, we have 4AB now. Instead of B, we have A. So, what we need? 4. Instead of A, 4AB into, what is B here? It is A. Okay. So, it is 16 A square B. So, answer is B. Okay. Now, what about this associativity of this star? So, the question is whether A star B star A, sorry, A star B star C and A star B star C both are same or not. So, associativity we need to check A star B star C, A star B star C. Okay, if these two are same, then we will say it is associative. So, what about this one? Is this associative or not? So, try both sides, and if both are same, then it is associative. Otherwise, it is not. Yes, okay. So, very quickly we will do the left side first. So, A star B is 4AB star C, and here right side A star B star C is 4BC. I am just applying the definition only. Now, again 4 into 4AB into C, here 4A into 4BC. Okay. So, what we will get? 16 ABC Here also it is 16 ABC. That's all. So we got everything is actually equal. Okay. So we will get this is associative also. Associative. It will be commutative also, right? So you can check that also, commutativity also if you want. It will be commutative also. Okay, now the question is, G is a set of all n by n matrices, okay, over Q. Over Q means the elements of like the matrices are coming from Q. So for example, we will have some A, B, C, D. So A, B, C, D, everything belongs to Q. This is a 2 by 2 matrix instead of n. So that is the meaning of over Q. G is the set of all n by n matrices over Q. Then the question is whether G is finite or infinite. Similarly, abelian or non-abelian. Can anyone tell? First, you can check whether it is finite or infinite. Okay, it's infinite. And what about abelian or non-abelian? Okay, let's first see whether it is finite or infinite. So given G, what is G? Let me write it very clearly. What is G? G means set of all matrices A11 etc. A1n, A21 to A2n etc. AN1 to ANN. Okay, because this is the n by n form of an n by n matrix, correct? So with each Aij belongs to Q. Aij means 1 less than or equal to I and j less than or equal to n. Okay, this is the given group G with the operation addition, matrix addition. That means like n reverse addition. Now, why it is a infinite group? Because Q, we know Q is like a countable set, but it is infinite. Okay, it is not finite. Okay, now for A11 we have infinite number of choices. Abelian, yes. For A11 we have infinite number of choices from Q. Okay, for the next element A12 there are also infinite number of choices. So for each of this n square element, we have n square elements here, right, in this matrix. So for each of this element we have choices from Q, like infinite number of choices. Okay, so it should be an infinite group. Now the operation in the G is given as addition. So addition means what? It is just like A11 to A1n etc. AN1 to ANN, and another matrix B is such that B11 to B1n, BN1 to BNN. Suppose it is like this. What we will do? We will add A11 and B11, the next element. So corresponding element we will add. So addition means it is the basically the addition is coming from addition in the Q only. Okay, A11, B11, both are from Q. So addition is actually commutative in Q. Okay, the operation is commutative. So if we are doing A plus B or B plus A, it is just like reversing the order, but it is commutative. So it is commutative. Okay. So it is an abelian group also. So it is an infinite abelian group. Again, one more question. Sn denote the set of all bijective functions on the set 1 to n. So we have already seen in the last week what is Sn. Sn is a symmetry group on n letters which contains all the permutations or bijective functions of the set 1 to n and given n greater than or equal to 3. Okay. So, whether Sn is finite or infinite, in the same way whether Sn is abelian or non-abelian. First of all, you can check whether it is finite or infinite. So, if it is finite, we have some particular number, cardinality we can say it is 5, it is 10 or some number we can say if it is finite. So, what is the cardinality of Sn? This we have seen in the last week actually. Sn means set of whole bijection from 1 to etc. n to 1 to etc. n. Okay. So, the cardinality of Sn means the cardinality of bijection. Yeah. The number of bijective maps from 1 to etc. n to 1 to etc. n. So, we have already seen that as cardinality of Sn is n factorial. Okay. So, okay, let me very quickly explain why it is coming. So, it will be easy for you to remember. So, in the first, like what we need to find is number of bijection. Okay, Sn means number of bijection. Yeah, how to find the order of symmetric group? Order means like it is finite, right? That is what you are asking, right? So, you are asking about why it is finite, isn't it? Okay, let me explain this. So, what we want is a bijection from the set 1 to etc. n to the set 1 to etc. n. Okay. So, if f is a bijection, suppose I am mapping 1 to some element. I can map 1 to 1, 2, 3, etc. n, any of the element. So, here I can map 1 to some element. It has n possibilities. Okay, I can map to 1, I can map to 2 and up to I can map to n. Okay, if such a map for 1 is fixed, now the next element is 2. Now for 2, I have n minus 1 choice only, because for 1 I have fixed one element, say some 5 or something I fixed. So other than that 5, I have some n minus 1 choices, right? Out of n, 1 choice is fixed for 1. So then I have for 2, I have n minus 1 choices there. For 3, so for 1 and 2 I fixed. Okay, for 3 I have n minus 2 choices. 2 choices already done for other 2 elements. So in the same way, if we are going for n, we have finally the last, for the first 1 to etc. n minus 1 element, we fixed one element. Okay, for the last element, so we have the remaining element from this n choices. Okay, so it is 1. So altogether, how many maps are there? N into n minus 1 into etc. 1. Okay. So this is the n factorial. This is the order of Sn, the number of elements in the Sn. Is that clear? Rashmi, is that clear? Okay. Good. So we got n factorial. So whatever the n I am giving to you, n factorial is always a finite element, right? So it is finite. So Sn is a finite group. Now the question is, now what is the operation here? It is the composition of function f composite g, g composite f, like that. So whether it is abelian or not, that means whether f composite g and g composite f are same or not. Yeah, non-abelian. Usually we know the composite function is not commutative but associative. Here also we can say it is just the bijective function and composition. So it may not be abelian always. So it is non-abelian. So it is better to give an example always. So let's see one example such that F composite G and G composite F are different. So usually let me take an element. So anyhow it is given Sn for n greater than or equal to 3. Actually for any Sn n greater than or equal to 3 it is non-abelian. Okay, so what I am taking is 1, 2, 3. Even though I have taken 1, 2, 3 cycle only, this is not from S3. I am taking it from Sn. Okay, what does that means? 1 is going to 2, 2 going to 3, 3 going to 1, and all the remaining element up to n goes to itself. Okay, that is the definition of, that is the 1, 2, 3. Now 1, 2, 3 I can write it as the product of cycles 1, 3, 1, 2. Okay, actually this 1, 3, 1, 2, both 1, 3 and 1, 2 are, these two elements are coming from Sn. What is 1, 3? 1 going to 3, 3 going to 1. All the remaining elements are fixed. Similarly 1, 2. Okay, in the same way I am taking 1, 3, 2. Here I can write it as the, so usually if we have a cycle, we will write it as the product of transposition in this way. First 1, 3 we will write, then 1, 2. Here also first 1, 2, then 1, 3. This is the like transposition, writing the product of transposition. This is the way. Okay, so it is 1, 2, 1, 3. So from here what we can say, 1, 3, 1, 2. If it is F, it is G. This is G, this is F, correct? Here F composite G not equal to G composite F. Why? F composite G is given as 1, 2, 3 and G composite F is given as 1, 3, 2. Correct? So both are actually different, right? The cycles are different. Here 1 is going to 2, here 1 is going to 3 and here goes 1 to 2. So these are different. So it is not abelian also. Now the next question is, given a group Z plus means integer with addition, and the mz is given as the multiple of m. Okay, so 0, m, minus m, and now 1, 2, 3 belong to Sn. What is the order of 1, 2, 3? Okay, what is the order of 1, 2, 3? For a particular element we are saying order means if how many times I am multiplying that to itself, we are getting the identity. Okay, that means the least number of times. For example, I have 1, 2, 3. I am doing again 1, 2, 3. Okay, so what I will get here is 1 is going to 2 and 2 to 3. So it is 1, 3. 2 going to 3, 3 going to 1 means it is 2, 1 and 3 to 1 and 1 to 2. So 3 to 2. Okay, so this is my this is my row. Okay, so this is row composite row. I got this. Now what I will do, row composite row composite row. So already I got what is row composite row. 1, 3, 2, 1, 3, 2. Again I am multiplying with the row, that is 1, 2, 2, 3, 3, 1. So here 1 going to 2 and 1 going to 2, 2 going to 1. So 1 going to 1. 2 to 3, 3 to 2, 2 to 2. Okay, 3 to 1, 1 to 3. Okay, so 3 to 3. So this is the identity. So if I am multiplying row with row, I am not getting identity. If I am multiplying once again row, composite, row, 3 times operation doing means I am getting the identity element. So the order of row is, now I don't need to go further. I got the smallest element such that row power n is identity. So that is 3. So order of row is 3. Okay, it is not n factorial. So what I am saying is the cardinality of Sn is n factorial. Okay, cardinality of Sn means number of such bijections in Sn. So this row is actually belongs to Sn for all n greater than or equal to 3. Okay, if n equal to 3, okay, this is the just row. Okay, if n greater than or equal to 3, what we need to do is for the remaining elements. So 4 to n, we need to fix it as itself. 4 to 4, 5 to 5, like that. In that case also, they are always fixed. So we just need to consider about 1, 2 and 3. So under 3 times operation, we will get the identity wherever row belongs. Like whatever Sn row belongs, we get order of row as 3. Okay. Okay. Question. Z plus is the group of integers, and the mz is the set of all multiples of m. So maybe you can check whether this is a group or not. Obviously it is a group, you already know that. For a given m in n. So which of the following are true? So first question is the intersection of 3z and 4z. Instead of m, we are having 3 and 4. So its intersection is a subgroup and its union is a subgroup. Which of them is true or false? Any idea? So this kind of in general we have seen in the class itself actually. One is true, yeah. Intersection is always a subgroup. And what about 2? This we have seen in the class itself. If like a proof is also there in the class. If there are, yeah, 2 is false. Good. So identity does not exist. Identity does not exist where? In which set? In which set identity is not existing? Okay, we will come to that later. So the result is if H1, H2 are subgroups. Okay, you can. Okay, it's fine. You can prove it. It's already given. Yeah, closure property does not hold for second case. Yeah, that's correct. So here also we will just see what is the group 3Z intersection 4Z. Okay, before that let me write what is 3Z. 3Z means all multiples of 3. And 4Z is all multiples of 4. So intersection means set of all elements which are multiple of 3 and multiple of 4. Okay, here if you are seeing only 0 is there, 3Z intersection 4Z. So clearly 0 identity element is there. So in the set list, okay, we are not seeing, but after some stage we can say after this, okay, let me a bit more. So 9, 12 and so on so. 4, 8, 12 and so on so. Okay, so the next element in the intersection is actually 12. What is 12? It is a multiple of both 3 and 4. Okay, so next will be 12. Here in the same way minus 12 will come. Okay, so it is actually it is 12 Z. Okay, this is the intersection and this is clearly a group or subgroup. Okay, so it is a subset of Z and it itself is a group. So it is a subgroup. Now, if we are doing the union, 3Z union 4Z, what we will get? For example, let me write some particular 0, 3, minus 3, 4, minus 4 and so on so. Let me list like this. Okay. For example, what I am doing is I am adding 3 and 4. Okay, this is also, if it is a subgroup, it is a subset in Z, okay, and it should be it is a subgroup only if it is closed under the operation, the same operation as the original group Z. So what is the operation here? It should be plus, because in Z we have the operation plus. So I am taking two elements 3 and 4, which is 7. 7 is clearly not in 3Z union 4Z. Okay, because it is not a multiple of 3, it is not a multiple of 4. So it is not in the union also. So this is not a subgroup, it is just a subset. So in general, intersection is always a group and union is always not, we cannot say always, but still in general it is not a group. Okay. Okay. Now the next question is, G star is a group and A is an element in G. They are not specifying what is this group and all, and it is just given that order of the element A is 30. So the question is, what is the order of A power 21? So to find this kind of like to solve this kind of questions, we have one formula. If order of A is given, what is the order of A power n? If you remember that, you can just do in 1-2 steps. So what is that formula? So that is a result again, that's also discussed and proved in the class. So I am not going to go in the details. So if order of A is n, so this is the result. If it is given order of A as some n, then order of A power m is n by GCD of m and n. Okay, here also it is like just an application of this result. So the same way like question will come in your exams also, just to apply this formula. So here order of A is 30, so n is 30. So can anyone do and tell us what is the answer? What we need to find is order of A power 21. So m is 21. So order of A power 21 equal to 10. Yeah, very good. It is just do the n by GCD of m. What is n here? Order of A. Order of A is 30. And GCD of m and n. M is 21 and n is 30. GCD means greatest common divisor. So that is 3, right? So the greatest value it goes both in 30 and 21 is 3. So it is 30 by 3. This is 10. So option C is the correct answer. Okay. Okay, so let's go to the, I hope it's clear. If you have any doubt in between, please ask me. Otherwise, we will go to the next question. Okay, again it's a very simple question. Suppose G star is a group. So the question is, which of the following are true? You can very quickly tell this. Whether first one is true or not. G is said to be finite if mode G is finite. Yeah. If like cardinality of G is finite. Yeah, correct. Both are correct. If G is finite, what we will like when we will say G is finite, if the number of elements cardinality is finite. So one is clearly true. And we have already proved in the class that identity element is unique. Identity element inverse. So these are actually unique elements. So it is not unique. This is a false statement. Okay, that's a false statement. So let's go to the next question. The inverse of I in 1 minus 1 I minus I under multiplication is okay. So it's given a set with an operation. There is a question in the assignment actually to check whether it is a group or not, I think. Okay, minus I. So here I am just asking about the inverse of I. Okay, before going to inverse, what is the identity? First tell me what is the identity here. It is 1, correct. It is 1 because if I am multiplying with any element, 1 into minus 1 is minus 1, 1 into I is I. So I am returning to the same element. So identity is 1. So if we are getting identity, the inverse should be the element such that I into that element equal to 1. So we know I square is minus 1. So I into minus I is 1. I into minus I. Okay. So what is this? I into minus I, that is minus I square. Since I square is minus 1, it is 1. So this is our identity. So the inverse of I is minus I. So many of you have told that. Very good. So let's go to the next question. It's set star be a group where star is defined as star be equal to a plus b plus 1 or a, b and z. So first question is, what is the identity? What is the inverse of an element A in Z? Okay. So you can check whether it is a group or not, whether all the conditions are like closure property, associativity. Only these two we need to consider because identity and inverse we will cover here. So that you can maybe check later. So the first question is, what is the identity here? So identity means what we need? A star minus 1 is identity. Okay, let's see what is the identity. So what is the identity? If E is the identity, if E is the identity, we don't know the identity. So we need to find what is the identity. So what we need is A star E should be equal to A. Correct? In the same way, E star A should be equal to A. So let's just consider one case. By definition, it is A plus E plus 1. Okay, A star B is A plus B plus 1. So A star E is A plus E plus 1. So it is A. So we can do the operation minus a, add the minus a on both sides. It is not just the cancellation thing. Actually cancellation law holds in the group. I think it is not covered. So what we will do is not just cancelling a from both sides. We will add the inverse of a on both sides, which is equal to minus a plus a. In the left side we are adding on both equation. Okay, so this is equal to 0, this is equal to e plus 1, so e should be equal to minus 1. Okay, so the identity is minus 1. Now if I am giving an element a in Z, what is the inverse of a? The operation is a star b equal to a plus b plus 1, and we got the identity as minus 1. Okay, now find the inverse of the element a. That is a star a inverse, you should get minus 2 minus a. Very good. Minus 2 minus a. Yes. Okay, let's see. Let b be the inverse. Let b be the, I am just notating as b. Okay, inverse of a. So a star b should be equal to the identity minus 1. We found the identity as minus 1. So a star b is minus 1. So a plus b plus 1 equal to minus 1. Okay. So what should be the b here? Here also we are not just taking a and 1 to other side. What we will do is add minus a this side, minus a plus b plus 1 minus 1. Okay. So what we will get is, so first we added minus a here, then minus 1, again 1 minus 1. Correct? So what we are doing is adding the inverse so that this term will get cancelled, this term will get cancelled, we will just remain with our required element b. Okay, it is not just changing from one side to another side. This is the operation. Okay. So what we are getting is b equal to minus a minus 2. Clear? So this is the inverse of a. Good. So let's go to the next question. It's a very simple question. Order of So I am giving an element in S3. So what is the order of this element in S3? So it's again a very simple question. What is the order of this permutation? Yeah, 2. So we know in the first case it is going to 1 to 2 and 2 to 1. So if I am doing the composition once again, 1 going to 2, again 2 will go to 1. So 1 will go to 1, 2 goes to 1, again 1 will go to 2, so 2 goes to 2. Okay, so 3 is going to 3 only in both cases. So let me just write very quickly, 1 2 2 1 3 3. I am taking the composition. What we will get? 1 to 2, 2 to 1. So 1 1, similarly 2 2, and then 3 3. Okay, so we got the identity S3, identity element in S3. So order of okay, actually this is nothing but the cycle 1 2. If you have given a simple cycle, then you can easily say what is the order. For example, what is the order of 1 3 4 in S4? What is the order? So what is this element actually? 1 going to 3, 3 going to 1, sorry 3 going to 4 and 4 going to 1 and 2 is there, 2 is going to 2 only because there is no mentioning about 2 in this cycle, right? So whatever is not mentioned, it is fixed. Okay, so from this cycle itself you can say very quickly what is the order of this particular element. Are you not getting? So if I am if I am doing composition, yeah, 3, very good. If I am doing the composition, what I need to do is do again. So we don't know how many times it will go. Okay, so here if it is a cycle, what we can do is we can very simply see how this work. 1 going to 3 in the first time. Okay, second time 3 going to 4. Okay, third time 4 going to 1. Okay, so in 3 times 1 is returning to 1. That is, what is that 3? It is the length of the cycle. Correct? So if you are just having in the same way 3 also. 1 time, 2 time, 3 time. Within 3 times it will return. Okay. So order of cycle will always be the length of the cycle. So this is a very easy thing to do. Now okay. Now let me ask one more question. 1, 2, 3, 4. What is the order of row? So here order of cycle is length of cycle. Okay, here it is not a cycle, correct? It is a product of 2 cycles. 1, 2, 2, 1. That is 1 cycle, 3, 4. Okay, this is also coming from S4 cell. So what is this? 1 is going to 2, 2 going to 1, 3 going to 4, 4 going to 3. So very quickly you can think how many times if I am multiplying I will get the identity element. So that is the order of row, right? Order of row. What is this? 2. Yeah, because in the first time 2 times I am multiplying means 1 is going to 2, 2 is going to 1. In the same way 3 going to 4, 4 going to 3. So only 2 times is needed. Correct? So order is 2. Now in the same logic, can you say what is the order of 1, 4, 1, 3? What is 1, 4, 1, 3? Yeah, this is the problem. Here what I have written is 1, 2, 3, 4. Both were disjoint cycles. 1 was going to 2, 2 was going to 1. It was completely disjoint from 3 and 4. But this what is 1, 4, 1, 3? This is same as our this element, right? This 1, 3, 4. Correct? If I am writing the cycle 1, 3, 4 in the product of transposition, what I will write? 1, 4, 1, 3. First this and then this. Okay. So we have seen order of this. Order of row is 3. We have already seen. Okay. It is not 2. If it is disjoint only, we can do like that. Okay. So if you are having a row which is not in the form of disjoint cycle, product of disjoint cycle, first understand what is that row, write the row and then see if it is a cycle, you can write it as the length, as the order. If it is not a cycle, what you can do is you can write it as the product of cycle and then you can find the order. Again I am going to the product of cycle only. So what is the order of row 1, 2, 3, 1, 2, 3, 4, 5. Here also I am writing it as the product of 2 cycles. Both cycles are disjointed, correct? Because no element from 1, 2, 3 coming in the second cycle and no element 4, 5 coming to the first cycle. Now Can you say what is the order of 1, 2, 3, 4, 5? Here I know if I am multiplying 3 times, then 1, 2, 3 will map to the identity thing. Okay, at that case I don't need to consider about 4, 5. It is 4 and 5 are fixed in the first cycle. Okay, so if I am multiplying 3 times, 1, 2, 3 will be fixed. Okay, 1 will go to 1, 2 will go to 2, 3 will go to 3. But in this case, if I am multiplying 2 times itself, what I will get? 4 going to 5, 5 going to 4. Okay, so 1 I need 3 times, 1 I need 2 times. So if I am doing 3 times, what will happen? 1, 2, 3 will be fixed, but 4, 5 will be interchanged still, right? So I need to do again and again. So what is the possibility? If I am taking the LCM of this 3 and 2, I will get the identity. Are you getting? So LCM of 3 and 2, that is 6. Okay. Okay, let me explain once again. 1, 2, 2, 3, 3, 1, 4, 4, 5, 5. And this is, okay, this is our row. The 2 cycles I am writing separately as the product. Here I can do 3 times. 3 times if I am doing, I will get identity. But here if I am doing 2 times, I will get identity. And if I am doing one more time, that is 3 times, what I will get? 2 plus 1, 3 times I will get means again that 4 and 5 will be interchanged. From identity, I will again go to the same thing. Okay, I will get the 4, 5 only. So I want to fix the 4, 5 also. 1, 2, 3 is fixed in the 3 times. So if I am doing 3 times, 1, 2, 3s are fixed. But 4, 5 is not fixed. So I will go to the 4th time. 4th time if I am multiplying, this will go to, this element will go to fixed. Okay, but 1, 2, 3 will again shuffle. So what I want is, whatever the times I am multiplying, it should be both a multiple of 3 and a multiple of 2. That is why I am taking the least common multiple. I want the least such value which gives, the product gives the identity. Okay, so that is why LCM of order of cycles. Again here I am saying the cycle should be the disjoint cycles. Okay, so if we are having the disjoint cycle, so in the first case also, let me show you. Yeah, whatever we have given is 1, 2 and 3, 4. These are disjoint. Why we got the 2? Here this is LCM of 2 and 2. LCM of the length of the 2 cycles. Correct? That is why we got 2. Here since it is 3 and 2, we are taking LCM of 3 and 2, that is 6. So that is how we can see, like, otherwise see, if you are writing this as a permutation, you need to multiply 6 times to get this. But just using this formula, you will get in one step what is the order of some particular permutation. Okay? Any doubt in this? If you have any doubt, please ask me. It's like a simple, simple understanding concept only. Otherwise, okay. So otherwise we can go to the next problem. Okay. I think I haven't done this question. So this is a true or false question. S3, whether it is cyclic or not. We have seen it is not abelian, right? Yeah, we have seen it is not abelian. So the question is whether it is cyclic. What does the cyclic means? There should be a, we have seen Z is a cyclic because one generate whole Z. Okay, so question is whether S3 is cyclic. Any idea? Yes or no? false. Yeah, good. It is false. Yeah. So the thing is, if it is cyclic, what we want is there should exist a element from S3 which generates whole S3. Okay. Now we will see what is S3 and what are all the elements. So the first element is row node, the identity. Okay. The next element is 1, 2. A very cyclic group is abelian. Yeah, very good. That is enough actually. Because in case if it is cyclic implies abelian. Okay. If this is cyclic, it should be abelian. But we have already seen it is not abelian. So there is no chance it is cyclic. Okay. So what about the converse? Does abelian imply cyclic? Anyone knows that? About this converse? Okay, next question we will go to that. Abelian implies cyclic or not. Okay, before using this one, okay, without using this, I will just tell very quickly why it is not cyclic, so that I can see what are all the possible orders, why it is not going to be cyclic. Yeah, converse need not be true. Yeah, we will come to that later. So 1, 2, 1, 3, 2, 3, 1, 2, 3, 1, 3, 2. Okay, these are the 6 elements. So we have seen all written as the like cycles. Okay, so for clearly order of row node is, as we have already seen, order of row node, it is the identity. Okay, so this is 1. And order of all the 2 cycles, it is 2. Okay, it is the order means it is just the length of circle. So order of 1, 2, 2, 3 and 1, 3 is 2. And order of 1, 2, 3 and 1, 3, 2, it is 3, because this is the length of cycle. So from this we can say it is not cyclic, because if it is cyclic, there should exist some row such that row generates the whole S3. Okay, but whatever the row I am taking, either after 2 times multiplying or 3 times doing the composition, I will end up in the identity. So I am not able to generate all the elements. Either in the generating, like if I am generating 1, 2 for example, I am doing the 1, 2, but I will get 1, 2 and then 1, 1 I will get, sorry, then identity I will get, correct? Because in the second time 1, 2 I am doing, I will get an identity itself. So if I am doing 1, 2, 3, you can verify this. What I will get? First I will get 1, 2, 3, then I will get 1, 3, 2 and then I will get identity. Okay, so 3 elements only. If I am again multiplying, I am going to repeat this process only. Again I am multiplying with 1, 2, 3 means I will get 1, 2, 3, again 1, 3, 2, again I. So whatever the element I am taking, I am not able to generate whole S3, correct? So this is not a cyclic. So or very easily, as we told earlier, we can say, since it is non-abelian, we can say it is not. And now every abelian group is cyclic. That is the question I was asking. That is the converse of the earlier statement. Cyclic. So what about this, true or false? So someone already told it is a false statement. So can anyone give an example? For this is false. Okay, this is false. That means an abelian group need not be cyclic always. So can anyone give an example of an abelian group which is not cyclic? Any idea? Okay, so we will give one example for that. That is our Klein-4 group. We have already seen in the last week what is Klein-4 group. So its group table is given like this. So 4 elements C, A, B, C under the operation star. So first row is itself because E is the identity. Okay, so whatever I am writing, you can see in the row, in the column I am writing in the same way. So it will be an abelian. So A star A is E, B star B is C, C star C is E, and this is CB, CB, AA. Okay, this is the Klein-4 group. So clearly you can see it is like if I am seeing along column, along row or along column, it is the same way. Okay, so what does that means? It is abelian because A star B is C, B star A is also C, correct? So this is an abelian group. Klein-4 group is an abelian but not cyclic. So this is a very simple example. There will be more example, but this is an example which is an abelian group but not cyclic. Why it is not cyclic? So it is not cyclic means we should say there exists no element which generate whole group. What is the group here? The set E, A, B, C with the given star operation. This is our star operation, right? So with this operation, the set E, A, B, C is called Klein-4 group. Okay. So from the group table, we can see it is abelian. Now, what is the generator of E? E generates only element E. Okay. So what is the A generates the element first A. Then we need to check A star A. What is A star A? A star A is C, right? From this table. A star A is C. Again if I am multiplying, what I will get? E star A. E star A is again A. Okay. Again I will repeat A, E like that. So A will generate AE only. In the same way, B will generate BE. C will generate CE. So we tried all the possible generators. Okay, each element we are considering, and it's like whatever we are getting, it is not a Klein-4 group. We are not getting the whole set EABC. We are getting the 2 element subsets only. So these are all the so what we can say, nothing generates the Klein-4 group. So it is not a cyclic group. Is that clear for everyone? Okay, not a cyclic group. Okay, good. Now, let me ask, what are all the subgroup of Klein-4 group? Can you say what are all the subgroup? E is a subgroup, obviously. First one is the identity itself is a subgroup, and the trivially we will say the identity the whole group. Okay, usually we will write V star. Okay, yeah, the whole group. For Klein-4 group, the notation is usually V. So V itself is a the whole group G. Okay, so the order of the Klein-4 group is 4. So the possible subgroup have the order either 1 or 2 or 4, correct? Because if some subset is a subgroup, we should have that order of that should divides the order of the original group. So possibility is 1, 2, 4. 1 means it is trivial group identity and 4 means it is the whole group. So what are all the groups with the cardinality 2? That is the only thing we need to see, and actually we have already seen that those subgroups having cardinality 2. What is that? Obviously E should be there because it is an identity. In the subgroup also identity should be there. Okay. Now only two elements is there. We got one element already. So what can be the other element? Any of the A, B, C can be the other element, EA. That is what we got, generator A. Generators are always a subgroup. Okay, generators. If I am taking one element, I am doing the generators. It is always a subgroups. So here also you can check identity is there. A inverse is A only because A star A equal to identity, right? Sorry, A star A equal to identity. So inverse of A is A itself. Identity is there, closure property is there, associativity is clearly there. Okay, inverse is there. So it is a subgroup. In the same way, EB, EC. So these are all the possible subgroup. Other than that, anything is possible. If I am taking AB, it is not a subgroup, right? Because identity is not there. I cannot take any other possibility. So these are all the possible subgroup of the claim for group. Clear for everyone? Ask if you have doubts. Like I don't know like how much you are able to grasp thing. So if you have doubt, please ask. You can unmute yourself and ask, or either you can chat also. Okay, by the way, one more thing, let me note here. What we can say is all these subgroups listed in this 3, okay, these are all cyclic actually. What I am saying is these subgroups are all cyclic, okay, but the original group is not cyclic. Okay, if the original group is not cyclic, we can have the subgroup either cyclic or not cyclic. But if the original group is cyclic, the subgroup will be always cyclic. Okay, here these are all cyclic, but V is not cyclic. Okay, just mentioning that's all. Now the next question is, find the generators of Z6 plus 6. We know what is Z6 plus 6. It is Z6 means 0, 1, 2, 3, 4, 5 under addition modulo 6. We have already discussed what is addition modulo 6. So the question is, what are all the generators of Z6 plus 6? So easily you can say one generator. Okay, one generator is very easy. What is that one? Generator means it should give the full set Z6 if like we are constantly adding that under addition modulo 6. What is a generator? Give me any generator. No, 0 is not a generator, right? Because 0 is not a generator. Why? 0, I am adding 0 plus 0 means again 0. 0 plus 0 plus 0 means again 0. I am not going to get the full Z6. Like actually not Z6, I am not going to get any other element other than 0. Okay, so 0 is not a generator. So someone has told already, 1 is clearly a generator. Because first we will start with 1. 1 plus 1 is 2. Again 2 plus 1 is 3. 3 plus 1 is 4. 4 plus 1 is 5. And what is 5 plus 1? It is not 6. Since it is under addition modulo, it is 0. Yeah, good. It is 0. So what we got? We got whole Z6. Okay. Now what is the, okay, now leave about that. Can anyone say any other possible generator for this? You can check, like 0 and 1 we covered. You can go through 2, 3, 4, 5. Let's see each and every element, then you will understand. So if I am starting with 2, then 2 plus 2 is 4. 4 plus 2 is 6. That means it is 0. Now what about 3? 3 means 3. 3 plus 3 is 6. It is 0. Now you may be getting one intuition, because 2 and 3 are actually some divisors of 6. So before 6 element, like at some smaller stage itself, lesser stage itself, we are reaching to 6 and we are reaching to identity. So that's covered, like we are covered a very less number of elements only. The reason is 2 and 3 are divisors of 6. Okay. Now what about 4? 4 is not a divisor of 6. So we will try. What is this? First is 4. 4 plus 4. What is 4 plus 4 in set 6? Yeah, 2. Now what is 2 plus 4? 2 plus 4 is 6 and hence it is 0. Okay, 4 is not a divisor. Still we couldn't cover all the elements of set 6. Now let us see 5. 5, if we are starting 5 and 5 plus 5 is 10. What is 10 in set 6? 4. Good. Now what is the next element? 4 plus 5? 4 plus 5, yeah, 3. 4 plus 5 is 9. 9 in set 6 means first divide 9 with 6. What is the remainder? We are getting the remainder 3. That is what we are writing as 3. Now what is 3 plus 5? It is 8. In set 6 it is 2. Okay, good. 2. Again we are doing 2 plus 5 will get 7. So what is the remainder when dividing by 6? It is 1. Correct? 1. Now 1 plus 5 is 6. That is 0. Okay. For 5 also we got the whole set. So what are all the generator? 1 and 5 are generators. Yeah. So now I will give one idea. What is the GCD of 1, 6 and the GCD of 5, 6? So 6 is coming from the set 6 and we got 1 and 5 are the generators. Yeah, this is 1. This is the reason why we are getting 1 and 5 as the generators. Okay, now you can see what is the GCD of 2 and 6. It is 2. Okay, this is GCD of 4 and 6. That is also 2. GCD of 3 and 6. This is 3. Okay, so if GCD, the relative, if they are not relatively prime, what we are getting is they cannot generate the whole set. Here 1, 6, 5, 6 are relatively prime. What does relatively prime means? The greatest common divisor of that elements is 1. If this case is satisfied, they are generators. If it is not, that means GCD is not 1. In that case, not generators. This is not just true for set 6. It is true for whole set. So if we are getting set n, we need to find the generators of set n, find all the elements k which are relatively prime to n. Okay, all such k below n. Okay, obviously it should be below n, above 0. Okay, all such k will be the generator of the set n. This is a basic result. You can just remember formula. Okay, so that will give you the like easy calculation without going through the all the all the subgroups. So whatever we are doing here is, it is actually a subgroup. This is a subgroup. This is a subgroup. This is a subgroup. Okay. So if I am like if one element is a generator, either we will get the full group. If it is not a generator also, whatever I am finding all the generating elements, that elements actually forms a subgroup. Here you can see, okay, in this element, in this case 2 for 0, what is the inverse of 2? Can anyone say? 4, good. Inverse of 2 is 4 because 2 plus 4 is 0, correct? So in the same way, you can verify all these are subgroups. So if I am generating a subset with an element, then obviously it will be a subgroup. When it will be the whole group, if the greatest GCD is 1 with this element, with this n, then at that case, that element will generate the whole group. Okay. Okay, general case I will explain once again. If we have Z(n) under addition modulo n, okay, we have done for Z6 with the addition modulo 6. The same way, if we have Z(n) under addition modulo n, okay, we will find all k in 1, 2, etc. n minus 1. So, what is Z(n)? Z(n) is actually 0, 1, 2, etc. n minus 1. Okay. Obviously, we don't need to consider the 0 because 0 is not going to generate the Z(n). Okay, 0 means it generates only the trivial group. So, we are considering all elements up to 1, 2, etc. n minus 1 such that GCD of k and n is 1. Okay, that means this condition is called the relatively prime. K and n are relatively prime. Okay, so if GCD of k and n equal to 1, then k generates the whole Z(n). Okay, that is what I was telling. If it is not 1, it will not generate. So if you want to find the number of generators or what are all the generators, find all the elements below n minus 1. Okay, such that GCD of that element with n equal to 1. Is that clear? Okay, good. That's all. So next we will go to now one simple question we will do. So the question is, find the cyclic subgroup of Z30 generated by 25. So every Z(n) is actually cyclic. We can say 1 always generates the whole Z(n). So it is cyclic. So Z30 is cyclic. So and again the subgroup of a cyclic group is always cyclic. Okay. So the question is, find that cyclic subgroup which is generated by the element 25. What is Z30? Z30 means 0, 1, 2, etc. 29. So 25 belongs to this Z30. We need to find the cyclic subgroup generated by 25. Obviously, if some element is generating means it is obviously cyclic, right? What we are doing? Taking a square, a cube. We are doing the same operation again with the same element. So 25 is the generator of the cyclic subgroup generated by 25. Okay. So okay, let me clear. What is 25? This is 25. Then 25 plus 25 under addition modulo 30. Okay. And we will do till we reaches the identity elements. So what is this element? This is a what is this group? This is a cyclic group obviously, because 25 generates all elements in this group. Okay, so we need to find what is that group. Okay, you will say what is that element. First we will start with 25. What is 25 plus 25? Anyone? Yeah, 20. 25 plus 25 means it is 50. What we are doing is in set 30. So what is the element? It is 20. So what is the next element? You can tell next elements. 20 plus 25. Yeah, 20 plus 25 means it is 45. In 30 it will be 15. And next element. Very good, 10. Because with the 50 I am adding 25. I will get 40, and from 40 in set 30 it is 10. What is the next element? Yeah, 5. Because 30 plus 25, sorry, 10 plus 25 it is 35. So 35 means it is 5. Now next element, 0. Good. Okay, so we got the group 25 generated by 25. Okay, can anyone say one more generator for this? From this you can very quickly say one more generator, an easy generator. 25 is a generator we have seen. Other than 25, any other element generates this group or not? Yeah, 5, very good. 5 also generate, because 5 plus 5, 10, then 15, 20, 25, 30. 30 means 0. So we are obtaining the same. Okay. Now next you can just try it as a homework. Does there exist any other generator for this 5 or this 25? You can just verify that, consider with all elements whether any of them generates or not. Okay, that is the that you can just do it as an exercise later. This question, this actually I could have covered in the last week. It is one question about monoid. So let me do it now. Okay, so do you remember what is monoid? D. Okay, okay. Okay, first let me explain what is a monoid. Monoid means just weaker than the group condition. Group we have the closure property, associativity, identity and inverse, correct? So if we are removing the inverse condition, then we will get the monoid. Okay, if we are having 3 condition, what are all the condition? Closure property and associative and existence of identity. So the question is, which one is not a monoid? So let's see the first option A. Okay. So Z plus, is this closed? Closure property satisfied there under addition? Yeah, closure associative identity. Yeah. For Z, closure is satisfied, right? If I am adding two integers, again we will get integer only. So it is satisfied. And associativity, that's also very clear because I am doing A plus B plus C or A plus B plus C. Both are same. So closure property is satisfied. Associativity is satisfied. And what about the identity here? What is the identity? 0. Very good. 0 is the identity. Okay. Sorry. This is also true. With 0 is the identity. Now, so these properties are satisfied. This is a monoid. Now the next thing is Q under multiplication. Again, closure is satisfied, right? If I am multiplying two rationals, again it is a rational, and associative also it is true. If I am multiplying A dot B dot C or A dot B dot C, both are same, right? So associativity is there. And what is the identity here? Yeah, answer is D. Good. Okay, in this case B, what is the identity? It is 1. So second option is also a monoid. C also, it just follows like a Q. Here also closure is satisfied, it is clear. Multiplication of two complex number is complex number. And associativity, A, just as in the earlier case, associativity also holds. And here also identity is 1. That is, if you are multiplying a complex number with 1, we are getting the same complex number, right? So here also T, true. Everything is true. And what about the third option? It is natural number with addition. Here, okay, many of you have already told it is D. That means D is not a monoid. If it is not a monoid, one of them is not satisfied, either closure or associative or identity. Which one is not satisfied in this case? Yeah, identity, good. Identity is not satisfied. Clearly we can say it is closure property is satisfied because sum of natural numbers is natural number. And associativity also, it is just an addition, associativity holds. So these two holds, but the third one does not holds. What is that? It is identity, existence of identity. For existence of identity, what we want is if A is an element in N, yeah, 0 is not a natural number. There should exist some identity such that A plus identity should be equal to A. So only possible case is 0. But this does not belongs to the natural number. So it does not satisfy the identity property. So in case if I am taking the 0 together, now is this a monoid? No. Yes, it is a. Now in this case it is a monoid. Is this a group now? No, because we have seen all the three properties are done, but the last property, existence of inverse, it is not there. So, no, it is existence of inverse is not satisfied because for some A, 0 is the identity. So, A plus some element should be equal to 0. What is that element? It is minus A. Okay. So that minus A is not there in natural number. It is just 0 in the given set N union 0. It is 0 and all natural numbers, positive numbers. So inverse is not satisfied. So that is why we will go further step like Z plus In that case, we will take all the inverse also. In that case, we will get a group. Okay, that's very simple thing. And again, let me. Okay, Z plus is a group also we have seen. What about these two? This is a monoid. Whether these are groups? P and C group or not? No. Okay. Why it is not a group? Anyone? Why it is not a group? We have seen closure is there, associativity is there, identity is there. But the problem is with inverse then, right? For any element positive A, inverse doesn't exist. For which element? For which element inverse does not exist? If I am giving 1, it has inverse 1. I am giving 2, it has inverse 1 by 2. But if I am giving you 0, yes, 0, then there is no inverse. Okay? Not a group in this case, but it is a monoid. What I am saying is not a group, since no inverse for 0. Okay, that is why we are going to the respective group. To make it as a group, what we will do? Q minus 0 with the multiplication, or C minus 0 with the multiplication operation, right? So that is the way we will refine it to a group. What is semi group? Semi group, I think one minute. Okay, semi group means only two conditions. Yeah, closure and associativity. Semi group means closure and associative property. Okay, so semi group is closure and associativity and a monoid. Okay, these two are there. Okay, now we will go to the next question. Okay, so the next question is the inverse of an odd permutation is odd, even, or either odd or even. Okay, so what is odd permutation and even permutation? Anyone knows what is odd permutation or even permutation? Permutation we know, right? Like the bijective map from the n-digit set. So 1, 2, that is, yeah, number of transposition. Yeah, depending on the number of transposition, we will say whether it is odd or even. So for example, this is 1, 2, 3. It is a permutation. How we will write it? 1, 3, 1, 2. Correct? So we have write it as a like product of transposition. It is a like transposition means cycle of length 2. In that case we have 2. Okay, 1 3 1 2 2 cycles of length 2 are there. So it is an even permutation. And what about 1 2 3 4? This is 1 4 1 3 1 2. This is an odd permutation. Now, okay, using this example, can you say what should be the, like, what will be the inverse of an odd permutation? Is this odd or even? It should be odd, right? So, for example, what we can see here is, sorry. So, here this one is an odd permutation. Second one is an odd permutation. Okay. Now, to make it, to get the identity 1 4 1 3 1 2, what I can do with 1 2, if I am again multiplying 1 2, what I will get 1 2 1 2. Okay, that means 1 2 2 1, and again I am multiplying 1 2 2 1. So what I will get 1 2 2 1 means it will go to 1 1. Okay, similarly 2 will go to 2. So this will give identity. Okay, next I can multiply with 1 3. So what I will get, okay, say this is 1 4. So here I will get identity. So what I am remaining is, what I have is 1 4 1 3 1 3 1 4. Again this will go to identity. Okay, so it should be 1 4 1 4. Again it will go to identity. So this one is actually an identity. So this is our given odd permutation. So the same way the cycles are reversed. Okay, order is reversed. So that is our inverse of that given permutation. Correct? So in every case, if we have the odd number, the same number of element in a reverse order, same permutation in a reverse order cycles. In a reverse order, if we are writing, we will get the product as identity. Correct? So in this case, what we have, the number of cycles in this case, we have same as the number of cycles in the given permutation. That is odd. Okay. So inverse of odd permutation is odd. In the same way, can anyone say inverse of even permutation? Yeah, it should be even. It is the same logic. Okay, because we can write it in the reverse way, so that we will get the identity. Okay, now let me ask one question. Okay, so if you have given some elements like 1 2 2 1 3 3, this we can write as a product 1 2. Okay, and for example 1 2 2 1 3 4 4 1, this we can write it as 1 2 3 4. That is product of two cycles again. Now 1 2 3 4 4 1 and 3 3. So what is this? This is 1 2 4. Okay, again write it as 1 4 1 2. Okay, here all what we are saying is any permutation can be written as the product of some transposition, some number of transposition, and depending on the number of transposition we will say whether it is odd or even. Okay, now what about the identity element in Sn? Is this even or odd? It is an even permutation. Very good. Now, if it is an even permutation, what we will say? It can be written as the product of even number of transposition. What is identity? 1, 1, 2, 2, 3, 3, etc. n. Correct? Here, okay, here in this case, I was having a cycle 1, 2, 4. Here also I was having some cycle in every case. So from there only I have arranged it in the terms of transposition. But here I don't have a cycle. How I can write it as the product of cycles, even number of cycles of order 2. Any idea for anyone? Then only I can say it is even. Like you might have already studied, okay, that is even, identity is even permutation, and even permutation forms a subgroup. Everything you have seen, but in which way you can write it as product of cycles of length 2? Anyone knows that? Can you think about that? How you can write it as product of cycles? Okay, I am writing it as 1, 2, 1, 2. What is this? This is going to 1, 2, 2, 1. So everything else is fixed. The same I am doing 1, 2, 2, 1. Everything else is fixed. So what I am getting? 1 going to 2, 2 going to 1. Okay, 1 going to 1. Similarly 2 going to 1, 1 going to 2, 2 going to 2. So everything else fixed already. Correct? I got the identity permutation. So this is how we will write the identity permutation as the product of even number of transposition. That is why identity permutation is a even permutation. It is not just convention. We can write. Actually, it is not the unique case. I can write in case of 1, 3, 1, 3 also, or 2, 3, 2, 3 also. In every case, I can write it as the product of two cycles, two length cycle only. Okay, not 3 or 5 or 6, maybe 4 it will be possible. 4 it is possible obviously. Okay, for example, I can write it as 1, 3, 3, 1 I can write into 2, 4, 4, 2. Because if I am doing 2 times means everything will go to identity, right? So what I am saying is, it cannot write in any sense, it cannot write as product of 3 cycles, 3 transpositions. Okay, that is why it is belongs to the even permutation. And also one more thing, AN is the collection of all even permutation. For even permutation, it forms a group. So I think it may be covered, or like maybe one exercise or something it was there. It forms a group. Now the question is, does collection of all odd permutation forms a group? So this is the next question. If we are collecting all the odd permutation, does it form a group or not? Even permutation forms a group? No. What is the reason? Yeah, no identity, because we have seen the identity is already in even permutation and it cannot be written as the product of odd permutations. Sorry, odd transpositions, odd number of transpositions. Okay, so the identity is not a this is not a group. Collection of all odd permutations. It is not a group. Okay. Maybe I will do one more quick question. Okay, one more question we will do and we will stop there. So we have seen what is the centralizer. Okay, is a question in centralizer. Actually, the similar question I think there is in assignment also. So I will just give a hint and stop. Okay. So question is true or false. Okay, so CA means we are collecting all elements from G such that which commutes with A, that is X star A equal to A star X. So whether CA is an abelian group or not for every A in G. Is this true? Okay, I am not giving the full proof or something for this, but I will just give you a hint. Suppose G is a non-abelian group. Non-abelian group. Okay. Okay. Now in that case, whether CA will be an abelian group or not. It should be for every A in G. Okay. Suitably choose an A. Suitably choose an A such that CA equal to G. That is possible to choose a such that the CA becomes whole G. Okay, since G we have taken as a non-abelian and we have chosen an A from G such that CA equal to G. So CA will be non-abelian. CA will be non-abelian. Okay, is this possible? Okay, if this is possible, we will get a counter example for this one. Then it will be false. Or if it is not possible, obviously it is going to be true. So start with G, a non-abelian group, and consider this case and verify this. Okay, I am not going to more details. This is homework, and if you are able to do this, you can solve one question in assignment also. So that's all for today, I think. So other than this, if you have any doubt, please ask me. We can discuss now, or else we can stop the meeting for today. Any doubt? Okay. Okay, then we will stop here today. We will meet next week, same day, same time. Thank you all and good night.